you have water molecules that want to form a crystal. So water molecules will try and trap smaller molecules within them. Now, the faster those gas molecules are moving, the more difficult it is to form hydrates. The slower the molecules, the easier to form hydrates. So basically, that translates to the higher the pressure that you have, the slower the molecules move. The lower the temperature you have, the slower the molecules move. So basically, it's just driven by water molecules trying to capture gas. And now you get three typical structures that are formed: structure 1, structure 2, and structure H. And you'll see a depiction of them. So typically, structure 1 is the smallest, so it captures small molecules. Structure 2 is then propane, isobutane, nitrogen, and so on. But basically, it's a cage, water cage that traps the gas molecules. And also, I'm going to be talking about gas hydrates in this presentation. We also have hydrates forming in the condensate oil phase, but that's a separate subject, but pretty similar. Now, the conventional strategy is that you typically have two curves. You have a hydrate dissociation curve, which you see on the right, and you have a hydrate formation curve, which is on the left. Anything to the right of the curve, the temperatures are so high, the molecules are moving so fast that water can't trap hydrocarbons. Anything to the left of the curve, as you go for higher pressures and lower temperatures, molecules are moving slowly, water can trap those molecules and form hydrates. And in the middle, there's a metastable region. Now, the traditional approach is if you always stay to the right, if you always stay to the hydrate-free region, you will never have a problem. So basically, that's how all design is done. If you're designing a system, make sure you're always to the right and you will never have a problem. But of course, in real life, you cannot guarantee that you are always going to stay to the right. So, for example, you have a normal operation, you shut the system in and you let it cool down. Well, if you let it cool down and say it's a cold winter's day or it's subsea, eventually the temperature is going to move to the left. So you start creeping towards the hydrate region. If you decide to blow down a pipeline, then there is JT cooling, which means the gas gets even colder. So sometimes it's not practical to always avoid. However, every design is pretty much based on make sure that you always stay to the right. Now, the way you can do that is either use hydrate inhibitors, and hydrate inhibitors will just move that curve further away to the left. So you can imagine this is with no hydrates. With no inhibitor. If you add inhibitor, you just shift that curve away from the left and make it more difficult to form hydrates. The other strategy is thermal, where you keep the system warm. So that's typically with insulation. Now, okay. Is the mic not working? Oh yes, so the standard strategy is avoidance. However, there are some missing metrics, which is if you do get hydrates forming, how much? Where does it form? How fast does it migrate? Does it agglomerate? Does it block? So really the question is, so what? You have hydrates. Is it the end of the world? So now if we think about rethinking hydrate management, the question is what happens beyond the curve? What happens if you drift into the danger area? Now typically for hydrate formation, you first need to have water molecules should stick to the pipe wall. Once the water molecules stick, you have an aqueous phase. Aqueous phase comes into contact with hydrocarbons, and you see the little white circles, and you've got hydrates forming. So you have buildup, then you have growth, then there's deposition of hydrates. Now, as hydrates start forming on the wall, you start getting something like stalactites. You'll have sort of, you can imagine icicles forming. However, because of the fluid moving, it breaks them. So you get sloughing. So there's all kinds of complicated kinetics built in to hydrate formation. Now, one key thing to note is that the hydrate dissociation temperature is not the same as the hydrate formation temperature. So just because you're in the left of the dissociation curve doesn't mean there's a problem. You could have no hydrates whatsoever. Everything could be fine. And even if you do get hydrates forming, if you're to the left of the second curve, those hydrates could just get transported down the line. So there is nothing to say that they are going to agglomerate and block and cause a problem, because it all depends. It's a multitude of variables that affect that. Now, the heart of this talk is then how do you take into account the kinetics of hydrates? And so there is a university in Australia, University of Western Australia, and they are the world experts in gas hydrates. And so there's a facility there run by Professor Zachary Aman, and really the heart of this work is the research done by UWA to actually build a kinetic model. So they built a test loop. I mean, it's a simple schematic there. I feel like I'm ignoring this half of the audience. So the hydrate, the kinetics model looks at hydrate formation, dissociation, phase distribution, wall deposition rate. So it independently calculates how the hydrates will kinetically form. We then take that information and put it into a multiphase flow solver. So whenever hydrates form, they form a layer. That layer then affects heat transfer. So the formation of hydrates will affect formation in the next time step. So what the simulation does is it does mass, momentum, and energy transfer calculations, thermodynamic calculations, and rewrites those answers back into the hydrates kinetic model. So this is really an integrated solution where you have an independent, I suppose, DLL or algorithm that looks at the kinetics, and then you have a multi-phase simulation solver which then puts back the process data back into the thing, and it keeps going round and round. So with this, you look at the formation rate, see how the formation rate affects the thermodynamics, and see how the thermodynamics affects the formation rate. So really that's the heart. I suppose that's the heart of the research. Okay, now here is a real-life example where you do not have the hydrates kinetic model, but you have an ideal process simulator. And so this system here was a large long-distance gas condensate pipeline, where the only measurements available to the operator were pressure and temperature. There was low water loading, but the topography is up and down, so there was liquid hold up. You've got water trapped in certain sections. Now this was an actual hydrate event that happened. So you see two lines here. You've got the yellow was measured and blue was predicted. So for an existing system where you have real life information and you have a real life online tool which is predicting what's going to happen, most of the time you have a perfect match. Here, suddenly the flow rate was turned down for whatever operational reasons, and the model matched the pressures. However, so it's a pretty good match. However, during winter, there is a risk of hydrate formation. And here there's a window where the prediction and reality differ. So the prediction said if you turn down, my pressures should fall. But the actual measured value didn't fall that much. So that raised alarm bells. So someone looking at it says, wait a minute, I should be seeing lower lower discharge pressures, but I'm not. Therefore, there must be something wrong. So immediately the operator injected MEG. As soon as the MEG reached the hydrate blockage, it cleared it, and again, the system matched. So this is what we have at the moment, where you look for differences between prediction and reality to tell you whether you have a problem. Okay, now we look at the predictive part of it. So here, the graph on the top is pure prediction. This is using the kinetic model that was developed at UWA, University of Western Australia. And what the model can predict is total amount of hydrates that you will form, how much of it will be transported. So the red is the suspended amount. So it says, I can calculate how much hydrates you have, but I can also calculate how much is transported and how much is stuck to the wall. So taking that model, reapply to an existing case, and here it's something similar to the earlier graph where green is the measured value, and oh man, this is difficult. Oh, I think I've got it on the next slide. Yeah, nope. So green is actual measured reality. Red is if you don't have any hydrate prediction. So for this scenario, if there are no hydrates, you would expect the pressure to fall. However, it's not falling. This is real life. And this is what the kinetic model predicts. It says, I know you're not in an ideal situation. I know that you have hydrates. Therefore, the model estimates that it somewhere comes between prediction and reality. Now, of course, this was just an example test case. However, these models can be tuned to better match. Now, you might say, the key question is, so what? So what is so good about predicting hydrate formation? And really, the answer to that is that if you can develop an online integrated multi-phase simulator, okay, which I'll say can be done, has been done, is being done, if you can tune the model to match operation, you can use an offline model to carry out a risk assessment to see if I were to lose, say, a MEG pump, if it was a very cold day or a very cold night, would it really be a problem or not? Can I live with it, or do I need to take major action? Now, typically, I know some operators will say, if I'm at the risk of hydrate formation, I will shut down. I will not take the risk. I will shut down. So if I lose a pump and my analysis says I'm in the danger area, I will shut down, fix the pump, and restart. Now, of course, if you shut down and restart even a single pump, it might take you 6 hours, 8 hours, 10 hours, 12 hours because you're online. So then you're losing production. And so the last point is you can use predicted time to blockage to decide whether you need to take any intervention or not. So we worked on a project with a client where we said, for about 24 hours, you will not have a problem. Don't worry. You can go, you can fix your pump, you can sort out the problem, you can get back online, and everything will be fine. You don't have to take a shutdown. So really what I'd like to suggest to you is that is the way forward. And of course, the savings are tremendous. You're talking millions, tens of millions, hundreds of millions of dollars. Basically, avoiding unnecessary shutdowns. Okay. So, thank you. If anybody's got any questions?
Have you any questions for Mr. Ashfaq? Yes, go ahead.
Question?
Go ahead.
Thank you very much, Ashfaq, for the nice presentation. Mahmoud Nazari, I'm from Qatar Energy Agency, Head of Flow Assurance. So one question is the risk of operation in the hydrate zone. So you are talking about the kinetics. Have you considered anything about if we operate in the hydrate zone and hydrated flows inside the pipeline? So in this case, any risk of the flow-induced vibration due to the larger amounts of the hydrate pieces inside the pipeline, or erosion risk, extra erosion risk inside the pipeline. These are other things that, not from the flow, from the mechanical part of the whole facility, it can impact the flow-induced vibration. For example, especially in the riser base, so these kind of formed hydrate, if they move inside the pipeline, they will make a lot of movement of the pipes, and it can go to the fatigue of the pipeline. So these are another risks that might be also analyzed for the hydrate formation.
No. Very interesting question. No, we haven't looked at that. And I think the reason is we didn't want to go that far, that there is so much that it will actually cause mechanical issues. So what we found is usually it will agglomerate in bends and it'll block them up. So what the software can do is it can say, if there is a risk, it's going to be at this particular location. This is the one that you got to be careful about. This is the one where you need to do remediation if necessary. I don't think we ever had a system where it's just a straight line and it doesn't block and it just gets carried through. But no, interesting question. But because that's easy, that can easily be done in the multiphase solver, because the density and the viscosity and the velocities, all of that is available, so that calculation can be done.
Yeah, that's my recommendation about the FID. So they are very important, especially in the riser base, for the fatigue of the facilities, that it will ruin everything.
Yeah.
The operators usually take care of that very much.
No, I've never heard of FIV from Hydrates, but yeah, I'll look into that. Thank you.
Thank you, Mr. Ashfaq, for the presentation. It's a lot of good information. Your last slide, please, can you go back to the slide where you showed the predictions? Yeah, there's a difference between the green line or curve and the blue. And you said the model can be tuned to account for this difference if there is any blockage.
Yeah.
So can you please elaborate more on how you usually tune these models? I mean, physics-based, or you just look at the behavior and then you just tune the model based on the data sets that you get? Or you study that from physics point of view? My name is Professor Ahmed Sliti from Qatar University.
Okay. So yeah, thank you, Professor. Very good question. So here, when you see a prediction versus reality, so that is a tuned model. So you can use an online training simulator, and there are simulators available. And I know because, of course, Wood sells one of them. So you can use simulation model for design, or you can use simulation model for real-time monitoring. So this approach is for real-time monitoring, where everything in that simulation can be tuned. When you do a design, you know exactly what you're designing for. Somebody says, this is the amount of gas I've got, this is the molecular weight, this is the composition. In reality, you have no idea what the composition is. So what you do is you run a model based on whatever information you have available. You look at reality, and if you see that the pressure drop is too high or too low, you can adjust the correlations. So that's the advantage of having a model where everything is tunable. You don't change the inputs. You just change the response of the system to match. So in this case, a system was tuned exactly to match reality. You see a difference and you say, I think there's a problem. Because 99% of the time I can match exactly. Suddenly now I can't match. There is a problem. So that's how this issue was picked up. So that simulation is tuned. Now, because it's been tuned to match, similarly, you can use that same approach to tune this. So here is just default properties. Sorry, not this one. This one, yeah. So here's real life. Here is simulation without any modeling of hydrates. It just assumes there's no blockage, everything is fine. Putting in the kinetic model, it actually comes between the two. It says, no, I know that there is a problem forming. Now, of course, in order to tune this, it would take a fair bit of effort, because now you have to induce a hydrate forming event, which is very difficult. But luckily, we managed to catch one, and so we can present this. So really, this can be done.
And usually, Mr. Ashfaq, when you tune the model, does this last in the future, or another condition will form and you have to go back and tune it again? Based on your experience.
So the only time you'd have to retune the model is if something has changed. So it will match, you get water breakthrough. As soon as you get, say, water breakthrough, all your temperatures spike and you see, wait a minute, I was matching temperatures exactly. Now suddenly they've gone up 3 or 4 degrees. So then you say, it could be water breakthrough. I'll tune the model. Do I match it again? Now, if you can match it over, say, 3 months, 6 months, 9 months, then you say, no, I've got it under control again. So yeah, this is a long-term online system, and it's been systems like these have been running for 20 years or so.
Thank you. This is Azad from the faculty of University of Doha for Science and Technology and Chemical Engineering Department. This is not a question, just a request. We have a few students from Chemical Engineering Department from UST, and I think we are not aware of the hydrates at this point in time. So can you please briefly explain what are the hydrates in your field, like especially oil and gas, and maybe a mini case study, how does it affect your whole process of the oil production?
Okay. Okay, so hydrates are a very strange phenomenon. It looks like ice. Now, normally you'd say, if my temperature is above 0 degrees, ice doesn't exist. However, hydrates can exist at 5 degrees, 10 degrees, 15 degrees. Suddenly, you have a system where ice is formed, where ice should not be possible. It forms, it blocks the pipeline. Once it blocks the pipeline, you've stopped production. Then the problem is, how do you dissolve this ice? Now, it's not really ice, it's a structure that behaves like ice. And what you have is you have water in your gas stream. And as soon as it comes into contact, if an aqueous film comes into contact with hydrocarbons, so you can have methane, ethane, CO2, H2S. Now, this is typical. Every gas field is going to have this. So if the conditions are right, you have an aqueous phase, you have hydrocarbons, which is always there, and you have the right conditions being all the gas is moving slowly. That means it's low temperature or high pressure, which again are normal operating conditions. The water molecule will trap the hydrocarbon and it'll form a crystal. And then that crystal grows. So you have water will stick to the top of a pipe. It comes into contact with hydrocarbon and you start getting crystals forming. Then those crystals grow, and they'll form, they'll break off, they'll form, they'll agglomerate, they'll form a blockage, blocks up your pipeline. This is one of the worst things, I suppose the second worst thing for any oil and gas development. First, of course, is corrosion, because you have a loss of containment. Second one is you block the system, and it might take you 1 week, it might take you 1 month. In some cases, it takes you 3 months to then get rid of this blockage. And the only way to get rid of it is to send a chemical down to break down that structure. So there is a hydrate dissociation curve. Everything to the right, you can't have hydrates forming. So you could almost think of it as if this is water, and you say, as soon as you go above, oops. Soon as you go above 0 degrees, ice is going to melt. Soon as you go below, ice is going to form. So this is very similar behavior. This is the hydrate-free region. Here you get hydrates forming. And so depending on whether the pressure and temperature are, I suppose, not amenable, but if you've got low temperatures and high pressures, if you're to the top left of this curve, you have a problem. And if you have those conditions and you have water in your stream, you know that that water is eventually going to make its way to the top of the pipe. It's going to form an aqueous phase. Forms an aqueous phase. The whole green is hydrocarbons. It will find methane, ethane, propane, isobutane, and form a crystal. And that crystal, it just blocks your pipeline. So it's a major, major issue. So what operators do is, I always want to be safe. I want to make sure I never, ever, ever go into that area, but you can't avoid it. There's always unexpected circumstances. And so, the heart of this talk is, it's not as bad as you think, because you may have time to fix it before it becomes a real issue. Just because they form does not mean that they will block.
Any other questions?
Thank you, Mr. Ashfaq, for a very interesting presentation. So my question is mostly about here in Qatar, in our gas processing facilities, where we see the hydrate formation issues. Let's say, I know some countries that they have neighbors, or they send gas through pipelines to their neighboring countries. Here in Qatar, we mainly export gas as an LNG, right? So we don't have that pipeline, problem. But we have also extraction from reservoir in the middle of the sea, and then we bring the gas to the mostly Raslab and plant and process it, right? So I want to see, we see this hydration formation here in Qatar mostly through this pipeline, or even within the plant through the transferring gas from one unit to another unit?
No, it's pipelines.
It's the pipeline.
Yeah. Because usually in the piping between plants, the velocities are so high, and it's very controlled. Whereas in the pipelines, the well supplying the facility, you can have a plant trip which blocks in the pipeline. It cools down, you need to restart, you need to vent the pipeline. So there's far more, I suppose, conducive disruptions in supply lines, big pipelines, as opposed to piping. Usually the conditions are never there. Now, of course, if you've got JT cooling, if you've got a high pressure system and you're suddenly letting down, okay, there is a risk. But usually the velocities are so high that the hydrates will form and just be carried through. But in pipelines, the velocities are slower. So you can imagine snowflakes will form, and then the snowflakes will stick, and then they'll slowly build up wherever you've got bends and dips. And in a pipeline, you'll have a high concentration of water somewhere. So in one of the slides where we had the ups and downs, at all the low points, you could get water drop out. So there's a high amount of water, so you get a much higher probability of hydrate formation. So usually, I haven't really come across such an issue for in plant.
Any other question? We have some time here. Like, okay. So yeah, this
Oh, yeah.
will be the last one, and then
No, please, no problem.
this will be the last question.
I wanted to give you time to have lunch, so I.
Ashfaq is also available, after the talk, so we can if someone has more question, we can.
No, I mean,
but you can.
if the students have got any questions.
Yeah. Thank you for your presentation. My name is Yusuf Douglas. I'm a senior mechanical engineering student in Qatar University. I just have a quick question regarding the tuning of the simulation models.
Yeah.
So currently, in companies like your company, how is tuning being done? Are like machine learning algorithms being used, or how is it?
At the moment, it's done by hand.
Manually
It's done manually.
until now.
But of course, what we also have is AI and machine learning, where we take the simulation and we run it 100,000 times and tell this brain, please learn how the system works. So that is a separate subject. So we've done that as well, where I don't want to run a simulation model to know what happens if I change this or change that, because the model takes too long. But because the mega brain has run 10,000, 100,000 combinations, it tells you straight away, this is what you get. So very good point. We could then use that to tune this.
Yeah,
But-
this is
but-
what I was thinking about, using this emerging technology and even a tuning which will make the tuning process much quicker.
Yeah. But the real challenge is you have to capture a really bad event. Now, we were just lucky that we happened to be there when we noticed this and said, look, there's a problem. Meg was injected. The simulation said it'll take, I can't remember the time, but it'll take 12 hours for the Meg that you've now injected. You weren't injecting it before because it was you didn't need it. That means expensive thing just to put it in when you don't need it. So it wasn't injected. We say inject it. We'll work out. It'll take 12 hours to get to the point where we think the blockage is, because again, it's got to reach. There's a residence time, and then so this was predicted that we thought yes, it's going to reach there by this time, and it did, and then the models aligned again. But I mean, if you had 100 of these, 1,000 of these events, then you could say, I guessed what the pressure should be, so we got it to there. So it's just to show that you can build that into the model. But tuning, okay, that is incredibly difficult. However, one of the benefits of this was you have got 12 hours, 18 hours, 24 hours before you will notice anything. Because up until then, it forms, but it just gets carried through. It's no issue at all. So don't panic. Go there, switch on the pump, everything will be fine. Whereas prior to that, the philosophy was, I am going to shut down. So this just allows more of a, I suppose, a reaction time.
So all the question coming from here. Any question from there?
Yeah.
No question. Do you wanna one question? Okay.
One question from over there. Yeah, you can speak out from there. This room is small.
I'm a student from UDST. Although we're still not very heavily into this topic. We did learn about line heaters.
Sorry, about?
Line heaters.
Okay, yeah.
So how is this just not different, just putting a line heater where it would be more hydrogen installation or something?
So this is a 200 kilometer pipeline, subsea. It could be across the desert, and your blockage could be 200 kilometers from where you are.
So this is mainly in the transportation line?
Yes, yeah. This is in the main line, and it could be anywhere.
Okay. Thank you so much.
But insulation is a way of keeping it warm. So one solution is, so typically in regions where it's incredibly cold. So if you go offshore Russia, offshore Japan, offshore Australia, for offshore developments, the sea temperature is really, really cold. So the minute the fluid stops flowing, your fluid is hot, it's coming out of the reservoir, it might be, 200 degrees Fahrenheit, but your sea temperature, I mean, I was thinking degree centigrade, it's 10 degrees. So 10 degrees is what? 18, like 50 Fahrenheit. So you suddenly go from 200 down to 50, then you have a problem. So then you use insulation. So that stops it cooling down.
Thank you so much.
All right.
So, Mr. Mahmoud, I think Mr. Ashfaq is available.
Yeah.
So, because we actually would like to thank QSTP because QSTP is, kind of arranging this part of thing, and as well as they arrange some, light lunch. So I invite everyone to have light lunch, and Mr. Ashfaq is available. Any question, you have time to discuss with him. And also, I see this is another time that many students, I would say many students from UBST, and I would thank you, UBST faculty and others, arranging this one. I see Dr. Seriti also from Qatar University. So maybe we extend, this kind of collaboration for the future, so that because you are the future engineers who will talk after a couple of years this here to so this is very good for you for knowledge gathering and thing. So maybe we can extend, we can do how we can do this type of collaboration more. But I would like to thank you everyone also, like I see some industry presence, and also finally we would like to thank you QSTP. So with that, I think with your permission, we can close today's session, and please enjoy some food outside. Thank you.
Okay, thank you, everyone.